So today's lecture is going to be on series parallel resistive circuits. So we're going to look at and remind ourselves the rules for each type of circuit, and then we're going to put everything together and start sorting through some problems and diagrams. So before we put these two types of circuits together, let's remind ourselves the rules for a series circuit and the rules for parallel. And what these rules are and how they interact is obviously going to matter today. So let's remember, in a series circuit, I total is equal to I1, which is equal to I2, equal to I3, so on and so forth. So current is the same throughout a series circuit. We remember that. Our total resistance in a series circuit equals R1 plus R2 plus R3, so on and so forth. Right? As that current flows through the series circuit, it hits each of those resistances, so we just add them up straight away. Our voltage, or how we find voltage in a series circuit, looks similar to our total resistance, but if you remember, it is a little different. So E is equal to V1 plus V2 plus V3, etc. That's one of the ways we can represent Kirchhoff's voltage law. Remember that E is supply voltage. That is what we apply to the circuit. Sometimes it's called the apply voltage. And for example, V3 would be a voltage drop or a volt drop. And so the supply voltage to the circuit will equal all of the voltage drops. If you remember, we can also represent it like this, which was more true to Mr. Kirchhoff's actual law, which was our voltage rises are the sum of our voltage drops, or 0 volts is equal to E minus V1 minus V2 minus V3, etc. And for our parallel circuit rules, we had I total now equals I1 plus I2 plus I3. It's going to equal the sum of all of your currents coming in and out of certain junctions and nodes. Okay, so what we could say is what goes in must come out. We'll be reminded more of that as we go through and solve some of these series parallel circuits. Our total was the one that had kind of a more unique equation. The equation that I use for our total is our total equals bracket R1 to the negative 1 plus R2 to the negative 1, etc. Close the bracket to the negative 1. Because 1 over R is equal to R to the negative 1. So to save ourselves a lot of 1/overs, I just do that. And that to me is a much simpler way to do it. If you like the way the module shows it, absolutely go with that way. Whatever works to get you the correct answer. And then voltage in a parallel circuit was just E equals V1, which equals V2. Our applied voltage is the same as, basically it's the same as each volt drop across each load. So with those in mind, let's put both of our concepts together. And let's start looking at a series parallel circuit. Now, if you remember in, well, both the other lectures, I was drawing current arrows around the circuit. Now, in a series circuit, it didn't always matter that much because once you found current, it was the same throughout the circuit. But as we start to combine series and parallel, these current arrows start to become really, or at least for me, it's a really important way of knowing what's going on. For example, we have a current arrow here. So this is coming from our source. It goes through the first resistor. So these first two current arrows will be the same because that's a series circuit. But then this series circuit hits a junction right here, and the current splits off in two different ways and then combines after this parallel circuit back into a series circuit. And so this 6 amp total is 6 amps at this resistor and 6 amps at this resistor, but as it goes into this node, it splits off because it has multiple paths. And then it comes back together. What goes in is going to come out. So the 6 amps that comes in here is going to come back out here and still be 6 amps. And it's going to carry on its merry way. Throwing pens around, sorry about that. So we can already note, or at least we should be able to notice, that in this, just this parallel circuit right here, there's 3 amps up top and there's 3 amps down below here, which tells me that R3 and R4 is the same resistance value if we added them together as R2, because our current is the same. And so if we wanted to, we could put R3 together with R4, we could add them up to equal R3, 4, because they're in series with each other. And R3, 4, what we could call this new combined resistor, is in parallel with R2. So if we wanted to combine or put together, get the total resistance of this parallel circuit, we could do R34 to the negative 1 plus R2 to the negative 1 to the negative 1, which is then going to give us R2, 3, 4, and we could say, as we get into more complex calculations, it might help us to say R234 is equal to Rx. Save us all those commas. Keep it organized, keep it cleaner. If I wanted to redraw this after doing this calculation, I could just draw one resistor, which would be, I could label that R1. The second resistor, if I was going to redraw it as a series circuit, would be Rx now. And then R5. That is what we're going to start to do when we want to simplify the circuits. If we wanted to just add resistance, if we want to get our R total, we're going to want to get our R total using a series circuit, not a series parallel. Okay, so as we go through and as you practice series parallel, you're going to start to simplify things into a series circuit maybe, and then you're going to start to, you're going to get some values from that, and then you're going to expand them back out to the regular circuit, to the initial circuit that you're given, I should say. Now, as you start to get questions and problems that have series parallel circuits, make sure you look at small parts of it first. It's very easy to mix up the rules for series with parallel, and then it's good to simplify things. It's good to look at one part of the circuit, such as R5, R6 in parallel with R7. simplify things and then bring them back out to the initial diagram, to the initial problem. And so let's look at this part right here. This is probably the most complicated part of this drawing, at least, because we have this resistor, which is in series with these parallel resistors, which are then in series with R8. And then we have series within this parallel, so on and so forth. But keep it simple. Let's just look at R5 and R6 for a second. We know we can just add them up. They're in series with each other. And then we can do our parallel resistance equation to put together R5, 6, and R7. And depending on the values they give you in the question, depends on what ways you're going to solve it. For example, if it gave me a voltage for R7, I know that the voltage at 7 is going to be equal to the voltage at 5, 6, because they're in parallel with each other. I could also say that the voltage at 7 is going to equal V5 plus V6 because they're in parallel. So the voltage on this part of the parallel circuit is going to be equal to the voltage at this part of the parallel circuit. I'm still going to have my voltage drops across each resistor that's connected in series. So if I were to add R2 and R3 in parallel to make that, one resistor in series with R1 and R4, I'm going to have a voltage drop here, I'm going to have a voltage drop across here, and I'm going to have a voltage drop here. But in this parallel circuit, I know that R7 is going to have the same voltage as R5 and 6. And it's always important to draw current arrows. As it gets more complicated, draw a current arrow coming into each junction, going through each resistor or load. It's a very helpful way to conceptualize things, pardon me. Always current arrows, always current arrows. If you ask me for help with something, and you haven't drawn any current arrows on the diagram, or drawn yourself a diagram, that's important. If they don't give you one, draw your own diagram. And then as you simplify it, redraw the diagram for how it's going to be after you, combine these resistors and combine these resistors. That's going to help you get more comfortable solving series parallel circuits. So here we go. We're continuing to get more complicated. Now, if we take this out, the circuit's not too bad. We have R5, which is in series with this parallel circuit, which is R6 and R7. But what the heck is going on back here? What is R1 in parallel with? Are R2 and R4, are these in series right now? I can't tell. What is R3 doing hanging out down here? This little guy. So start out, let's draw current arrows. Remember that these are not going to be unsolvable unless they give you no values. So current arrows, current arrows, current arrows. Well, let's start looking at and thinking about where the current leaves, where it comes back together. What does that mean? Is that I total? Is that a combination of different I values? So let's look at these three down here to start. We know that the current comes in here as I total, and we know it comes back here as I total. We know once it hits this node, it's going to split off three ways. And then we can see at this node, it combines from two ways back into I total. And so if we look and we just pick one resistor, let's not pick R1 because it seems like it's in parallel with a whole mess of things. we can see that our current arrow goes here, and it comes here, and then it comes back to go here. So we could call this one right here I23 if we wanted to. We could call this arrow I2, 3, 4, and this is I1, right? Because this current arrow is the current from this R3 and this R2. So that tells me that the current at I4, or the current that's going to go through R4, I should say, is going to be the same current that goes through 3 and 2. So that tells me that R4 is not in series with R2 exactly. But I can see that R2, if I just kind of put my hand over other parts of the circuit, I can see that R2 is in parallel with R3. So if I put those two together, and I get a resistance of R23. I won't do every calculation in here, but let's just add those together real quick. Show you on my calculator in case you forgot from a module not that long ago. So it would be 6 for R2 minus 1 plus 12 for R3 minus 1 to the minus 1. It's going to give me 4 ohms, so R23 is equal to 4 ohms. So then I could redraw those put together. I can redraw that down here. So I know that it still goes up to R1. But now instead of R3 hanging out down here, it's just going to come through R23. That's going to carry on to R4, and that's going to join back up. So now by redrawing this, after combining R3 and R2, I can see that R23 and R4 are in parallel with R1. So I can add these two resistors together to make that look like, try a little node there. To make it look like two resistors in parallel, which will now be R2, 3, 4, and R1. And then I can do that again. And then I would have R1, 2, 3, 4 would be one big resistor in series with R5. And that's going to be how we start to deal with resistance in a series parallel circuit. We're just going to do parallel calculations, simplify it down to a series circuit, and then if we want our R total, we know we just add up all the resistances in a series circuit. Now, as we start to talk about current and what's the value of current at specific areas, we're going to start to draw current arrows frickin' everywhere. You're going to hear me say current arrows probably a few more times within this lecture. So we see that the current comes to this node. It's going to go through this resistor and this resistor. So that means my I total, I could get it by just adding these two together. I also know that my I total will be right here because I can see that all the places it goes in this big mess of a series parallel circuit are all going to combine back up right here. So I know that from this resistor down here, the current, some of the total current is going to hit this node, come down through this resistor, come back up, and it's going to combine with this current, which is then going to combine with this current. So after these two currents meet at this node and carry on, they're going to meet this current, which is going to meet with this at this node, right? So on and so forth. And then the more current arrows you draw, keeping in mind that in a parallel circuit, current's going to start taking all these different pathways because it can, because current likes to be like that in a parallel circuit. So it's going to, every junction, every node, the current's going to split off and go all these different ways. And then as it continues to flow through the circuit, it's going to continue to join back up. Now let's talk about voltage. So if you remember from our parallel circuits, we didn't have these values of resistance out here. We were just talking about these two voltages. So you might be thinking, oh, the voltage here and the voltage here is the same. No, because we have these volt drops that are going to essentially represent volt drop on the wire, the voltage, the line loss, we might call it. Now your module talks about these plus minus values and kind of basically you add the E and then you minus V1 and then you just kind of follow. I'm just going to look at it as following the current arrows and remembering that in a series circuit, my voltage rise, this is my voltage rise, the rise in voltage comes from the applied voltage, or you could also think of it as the rise in voltage comes from all of the applied voltages. But in this situation, we only have one applied voltage. If this is our source of energy and we had a second source of electrical energy over here, then that would be another voltage rise. But it's not. These are all just voltage drops. And so if I think of it like a series circuit, and I kind of forget about this guy in the middle right now, then my E is going to be equal to V1, and then I'm going to carry on. Okay, yeah, some current goes down there, but I don't care right now, plus V2, and I'm going to keep going around like it's a series circuit, plus V4, and then I'm going to keep going around. I hit this guy, plus V5, and then I'm going to keep going, and this is a parallel thing, so I don't care. I'm going to follow this series circuit, plus V6. And that's going to give me E. Pardon me. If I wanted to figure out V3, well, I'm not going to really care about this half of the circuit. Because if I wanted to figure out V3, I would just follow this as if it were just one series circuit. Because I know that in a series circuit, I can calculate a specific volt drop like this. I can go, hey, I want to know V3. So I would take E minus V1 minus V6, and that's going to give me V3. I would just follow this around like it's a series circuit, even though it's a series parallel circuit. I'm going to break it up into small parts, use the formulas in the math that I know. I'm going to put those values in, and then I'm going to expand back to the full size of the circuit. Because if not for V2 and V5, V3 would be equal to V4. But because there's a volt drop here and here, they're not equal to each other. Because it's now a series parallel circuit, we're not looking at just parallel circuits. And this is honestly going to be a bit more... this type of circuit is a bit more real world, because even though we don't really hook up a resistor in series with a load, we often don't do that because we don't want significant line loss. This type of volt drop does happen because of the distance that we run our wires sometimes. So if you run a wire too far, you're going to have too large of a volt drop on the wire, and then the load that you're trying to power might not have enough voltage because it's too far away from your source. So while we don't really always hook things up in series parallel. The series parallel concept is a good way to sort of highlight real-world circuits. So here we have another series parallel circuit. I'm just going to start drawing current arrows because that helps me conceptualize what I want to look at, what I need to look for, because my current splits off there. But in terms of voltage, I can already start to look at, well, I know V3 is going to have the same voltage as V2. And I can follow my current through this path, pardon me. And I'll know that in a series circuit, because this is one series circuit, I'll know that whatever the source voltage is will be equivalent to V1 plus V5 plus V6. Because V5 is in parallel with everything with these three. So that means I could also say, well, E is equal to V1 plus V2 plus V4 plus V6, because that's also one series circuit. So if I follow it around again, E would be equal to V1 plus V3 plus V4 plus V6. And it's going to become a bit of a fill in the blanks type of math solving. What variables does the question give you? And what can you solve based on those variables and based on what you know about how the circuit behaves? Because I'll also know that the current at I4 is going to be equal to the current of I2 plus I3. I know that total current here is equal to total current here. And I know that the total current here would be equal to the current of I5 plus the current of I4. But I know that the current at I5 is not equal to I1 because it splits off here, because the current arrows tell me, nope, some goes here and some goes there. So across I5 is not the total current, because there's a node. Every time you see a node, you know that current splits off. So here we have, spoiler alert, another series parallel circuit, of course. That's what we're doing today. And this one actually gives us enough information to solve the whole circuit. If we wanted to know all of the volt drops, all of the current values, our total, whatever it asks for, this gives us enough information to solve everything. What we would do, since the first thing I notice is there's no current values, but I know that current here would be I total, same as the current here would be my I total. Great. And I total equals E over RT. So I could not just use 120 volts divided by 3, because that would be E over R5. But I could start combining resistors together. R1 and R2 are in parallel with each other. So if I can put those together, that combined resistor, that big resistor, R12, would then be in series with R4. And so R1, 2, 4 is in parallel with R3. We just keep combining them until we have the value 4, R1, 2, 3, 4, which would then be in series with R5, which would give us our R total, which then we could use and calculate I total. And then we could get V5 would be equal to I total over, or just, which is I total is the same as I5. We would do I5 over R5. We would then know that our voltage drop across R5. And so once we know that volt drop, we would know the volt drop across this whole parallel circuit. And we would know that the volt drop across 3 would be equal to volt drop of 1, 2, 4. Pardon me. I could also say, well, yeah, I know E is equal to V5 minus V3. I know that V4 is going to be equal to, V4 would be equal to V5 minus either V1 or V2, because these two resistors will have the same voltage value. But these two resistors are in series with R4. So whatever V5 voltage is, that value is going to be shared between these two, this resistor and these pairs of resistors. And so it really becomes remembering the rules for solving a series circuit. Remember the rules for solving a parallel circuit, and then applying them to specific parts of the circuit until you just fill in all of the values. And then as you get going, as you get more values, as you get, for this one, for example, once we had our I total, okay, well now we can just start solving so many other things. Then we can get V5. Okay, I have V5. That means, E equals, E would equal V5 plus V3. Pardon me. V5 would equal E minus V3. Apologies for that if that confused you. And then we would know our current that would be coming down here once we get the voltage across R3. And then we know we have current here, so on and so forth. Now, here's another way they might draw a series parallel circuit. Don't be intimidated by the fact it looks a little different. You do have enough information to solve this, right? We know that our I total will come in here. Some of that current is going to drop down to load 1. The rest of that current is going to carry on its merry way. And it's going to say, hey, I got load 2. I'm going to drop some current down there to feed you. And then whatever I have left is going to go through through load 3, and I'm going to pick them back up on my way through. Okay? I total is like a bus service, but as soon as it drops you off, it's going to pick you up. It's never going to leave you. Never going to leave you hanging. I total always picks it all back up for these types of equations. Okay, so don't be intimidated when they start giving you these crazy looking equations. So let's solve this one together. You may start to see some of my values. This is just a problem out of the module. Some of my values might be a little different from what's in the module. It's basically because, well, I'll just show you right here. This calculation they did is not 0.68, it's 0.67. I'm kind of assuming they left many more decimals for this current value, but if you put that into your calculator, you'll see it's 0.67, not 0.68, which does give very slightly different numbers. We don't really care if the numbers are slightly different, as long as they're correct, as long as we solve it in the correct way. So let's look at what we have. Obviously, we have a series parallel circuit. We have a resistor over here. We have a resistor over here, which is getting some current. They already put the current arrows on for me. Love it. Module must have known that I was going to do that anyways. It also gives us these values up here, which are beautiful. Look at that. We already have I total. Damn, that's going to save us some time. We have R total. Don't really care because I have I total. Whatever values and variables you want to use to solve the equation, it doesn't really matter. Sometimes there's a variety of decimals depending on which value you use, but a variation in decimals should not give you the wrong answer. And so I can already go, okay, well, V7 is going to be I7, which this is the value of I total. So I7 and I total are the same thing. They gave me the I total up here. Beautiful. I'll use that. V7 equals I7 divided by R7, which is going to equal that value I was just talking about, 110.67 volts. Okay, so I know that there's 120 volts as a source voltage, and I know that this last resistor, it has a volt drop of 110.67. So if I kind of go big picture and just look at the whole circuit, I know that R7 is in series with everything else. From R1 to R6, this whole part of the circuit is in series with R7, which means whatever 120 minus 110.67 is, that value gets dropped across this whole circuit, or this whole part of the circuit, pardon me. So that means if I'm looking at R6, which is in parallel with everything in this part of the circuit, that means that the voltage drop across 6 is going to be equal to E minus V7, which is going to equal 9.33 volts. Cool. Awesome. That also means I can figure out I6, which is going to be equal to V7 over V6 over R6, pardon me. So that's going to be my current is 3.11 amps. And so you'll see in your module, these numbers are going to start to be slightly different. As long as you're using the correct values and getting similar answers, it's not really going to be a big deal. So with that said, I know I have 3.11 amps right here, right? Because this is I6. So I can take, this is I1, which is going to be equal to I total minus I6. Thanks to my beloved current arrows. I know that the total current comes in here. This is coming from my source. And so with my total current coming in here, hits this node, it's going to go this way, and it's going to go this way. Well, I know how much is coming down here, and I know how much is here, so I know how much is going to go through here. So my I1 is going to be equal to 0.579. Wicked. So now I can figure out my V1, which is going to be 5.79 volts. Beautiful. Look at that. I already have these three completely filled in. Awesome. I can even, if I wanted to keep in mind, I can say, sure, I7 equals 3.689 amps. But I already know that because it's written up here, but if it helps you remind yourself that the total that comes in here is going to come back out here after they join up at this node. So now I know that coming through resistor 1 is 0.579 amps, which is not very much, but all the same, that little bit of amperage is going to come to this node, and it's going to split up 3 ways. But I don't know how much goes each way. And I don't know how much is coming from R5 to join up with R6 in terms of current. And I don't know what's going through R4, although I do know that I total would be the current from R6 plus the current from R5. So this current arrow, I could call it I5-6, but I don't have the current for 5 yet. So this is one of those moments where you might start to feel a little stuck, but let's just go back a bit, start to think, what's in series, what's in parallel. I know that R1 is in series with R2, 3, 4, 5, which means the voltage drop of R1, 2, 3, 4, 5 is going to be the same voltage drop as R6 because it's in parallel with R1, 2, 3, 4, 5. So if I have the voltage drop across R1, I can figure out what's dropping across these resistors, and I can look and see that R5 is actually in parallel with R2, 3, 4. It's drawn a little weird here, but all the same, this point to this point is going to measure the same voltage as this point to this point. So I can say, well, V5 is equal to V6 minus V1, which is going to give me 3.54 volts. Sweet. Now I also know that I5, thanks to that voltage, I5 is equal to 0.295 amps. Wicked. I also know that I4, well, I know, but now I can solve, that I4 is going to be equal to I1 coming in here minus I5. Because whatever comes into this node is going to go 3 ways. But these 2 current arrows are going to combine at this node before R4. So I know that the current here is going to be equal to this current minus I5. So that equals I1 minus I5. I apologize if my writing is not visible. These can start to get really messy if you're not careful and organized. I'm doing this in pen because I believe in myself, but I highly recommend doing these in pencil. Otherwise, if you make a mistake, you basically just have to throw out the whole piece of paper. Anyway, so I4 is going to be equal to 0.284 amps. Awesome. That also tells me, since I know that R5 is in parallel with 2, 3, 4, that tells me the volt drop of 3.54 is going to be dropped across this circuit, but these are in series with each other. So with the current of R4 now, I can say V4, or I can solve for V4, which is going to be 272 volts. And since I know that 3.54 is the same as the voltage of 2, 3, 4, but 2 and 3 are in series with 4, so that means this 3.54 gets dropped across this whole part of the circuit. That means that V1, which is equal to V2, they're just in parallel with each other, is going to be equal to V5 minus V4, which is going to give me 1.268 volts. Just a tiny little voltage. But nonetheless, I can take that voltage and I can solve for I1 and I2. So I2 is going to be 0.2536. Just use all those little decimals. If you want to round to 3 decimal places, that should be more than enough. You can also do 2 decimal places if you would like. I'm a bit of a paranoid guy, so I like to do 3 or 4 sometimes. And I1 is going to be 0.0634 amps. Very tiny. And if we remember back to just the general concepts of resistance and current, if we look at R2 and R3, we see that R2 has a larger ohmic value than R3. Oh, sorry, these are supposed to be 2 and 3. My apologies. Those are labeled wrong. Which means that, which means that V2 equals V3, and then which equals 5 minus 4. Sorry about that. These are 2 and 3. My apologies. 1 is back here. Anyway, we see that resistor 2 is 20 ohms, resistor 3 is 5 ohms. So we would expect a smaller current value at R2. And we also just proved that mathematically. It has a much smaller current, even though they're both quite small amounts of current. So, remembering those kind of concepts, remembering all the rules, remember that Kirchhoff's voltage and current law, as well as Ohm's law, the reason we call them laws is because when we apply them correctly, they're pretty much always correct. That's why they're laws, is because they've held up after all these years. So, that's series parallel resistive circuits. Keep your stuff organized. Draw your current arrows if they don't give it to you. Draw a picture, simplify the picture, and redraw your current arrows. Keep everything organized. Can't say those two enough. And best of luck. Ask me if you ever have questions.